Good afternoon, everybody. Thanks for coming to a special seminar today. Not the usual Friday afternoon beer drinking contest, but I want to welcome you all to a jointly hosted seminar by the Newell series of Florida Sea Grant from the University of Florida and the College of Marine Science. Have a couple of guests today. The fellow walking there is Kai Lorenzen. He's a faculty person many of you may know at University of Florida and works in a number of fisheries-related areas. And our special guest is Dr. Verena Trinkle. And Verena comes to us from IFREMER, which is the French equivalent of NOAA, and she works in the quantitative fisheries group in the city of Nantes, which is on the edge of Brittany. I've known Verena for 18 years, I think we said, when she was just a young person. I wasn't. And so, Verena's worked on a variety of different fisheries-related projects since sort of coming into the field. She's done work on use of fishery acoustics. She's done line transect methods with underwater video, and she's done a lot on ecosystem indicators. And so she's published widely in the field. And we're really lucky to have her visiting us today. Her talk this afternoon is Identification and Analysis of Functional Groups in Ecosystem Modeling. So with that, it's all yours.
Thank you very much. Thanks for coming, and thank you, Raj, for inviting me to give this talk. So what I'll try to do is to give you an overview of some of the work we've been doing with respect to functional groups in ecosystem modeling. So it's going to be sort of a tour de force of different projects. But first of all, just to introduce you to IFREMER, for those of you who don't know. So IFREMER, as was said, is the equivalent of NOAA, and we have stations and institutes all over France, but also in overseas France, not only in mainland France. And the main remit of the institute is to do applied research, everything to do with the sea, and also to provide policy support. And we do a lot of data collection for monitoring purposes, from fish to coastal to seawater to shellfish contamination, whatever, anything to do with the sea. And then the main themes are around those to feed into those things: fisheries, coastal deep sea systems, physical oceanography, geomorphology, and underwater observation systems. There's also a big engineering department actually developing observation methods. And as was said, I work at the research group. Sorry, I got confused by it. Okay. In my research group, we are developing methods and carrying out research to feed into stock assessment, but also a wider ecosystem assessment. So it's quite a small group. We have different themes. Actually, it varies because over the time, but the main objective is basically to carry out ecological research and provide methods for stock assessment and ecosystem assessment. So in my talk today, I will be having two themes. The first one is about defining functional groups, and I will be talking about different methods. And then the second part is about modeling functional groups in a way. The first one is in a way static, and the second part is the dynamics. So the first part. Well, when we talk about functional groups, of course, the first question is, what functions are we talking about? Which functions should be used to create these groups? And basically, what a lot of people have been doing, and we as well, is that there are sort of two kinds of groups, the so-called effect groups and the so-called response groups. So the effect groups, then you come in from the perspective that what is the effect of a given group on the ecosystem, and individuals or species are grouped based on having a similar effect. Whereas when you're coming from the side of a response groups, it's groups, individuals that respond similarly to the ecosystem. There are different ways of actually creating these groups then. A lot of people, I would call that use the expert approach. Basically, they want to create groups, which are in this case predation groups, of species, individuals that have a similar impact. So we will define top predators, piscivores, planktivores. And then those are the groups using expert knowledge, diet information. So that's it. It's sort of, there's quite a lot of subjectivity here to actually what you group and how, actually also how many groups you have. Now, a different way of doing is to say you want to have it more objectively. So one way here is to use morphometrics. And also this is a field people have done for quite a while. And it's been established with respect to this predation that there are different sub-functions where you're precise in type, swimming capacity, type of approach in space. And these relate to actually morphological characteristics of fish, basically. It works for fish. It doesn't work for shellfish or anything else. It works for fish. So basically, using different morphological characteristics like the mean mouth diameter or relative gut length, then these inform on the potential an individual has for what he can feed on. So using this approach, we have collected data on individuals and measured these morphometrics. We use cluster analysis to create those functional groups. And so this is the result. In this case, you see here, these are the species we've worked on. So quite a list, so different fish species. Because we used both morphometrics and size, here you get the size distribution of individuals, and then here you have, in this case, 11 functional groups. And I guess one thing which is sort of particular about this study is that for a given species, as the individuals grow, they change, or they can change the functional group because there's a size aspect to it. And so basically, yes, the same species can be in several functional groups, and the change will happen at a certain size. We then wanted to know, okay, we've used this sort of objective method to grade groups, but how does that compare to what they actually eat? Because this is about potential. The morphometrics is providing the potential for feeding, but how does it compare to reality? And so we compared to actual diet, and we found that, okay, these groups explained, well, not that much, 28% of the actual observed diet, but it was more than double than what you could explain if we just used the same number of size groups. So this is, I guess, relevant when you think about how you should model an ecosystem, because as you know, or you might know, at the moment it's very popular to use size-based models where only size matters, nothing else. And just this simple comparison shows that size is not everything. I mean, morphometrics isn't everything either, but you get more towards really explaining the actual diet. Now, in our application is in the Mediterranean Sea. So again, we use morphometrics, but in this case, we only use the morphometric measurements. And then we created we did another cluster analysis. Because it's different species, that's why we had to restart in a way. So in this case, we had 72 fish species, and then we came up with 8 functional groups here. And you can just see here how they actually can be divided into the more benthic species, demersal and pelagic, which just shows you already, okay, within the morphometric groups, there is also you can identify the different habitats the species are living in. Then we wanted to use this now to look at the food webs in the Mediterranean Sea to say, okay, we have these functional groups, and how have they changed over time? What are their spatial patterns? So basically what we did is we used survey data from bottom trough surveys that has been carried out in a coordinated way throughout the whole Mediterranean Sea for the 15 years. We used this data to calculate changes for each group, the change in biomass. Then we used PCA to cluster areas with similar group changes, and then we asked the question, what are the environmental variables that explain the change? So basically, what we found is, so I guess you recognize this is the Mediterranean Sea, France is here, this is Spain, and then here's Greece. So the colored areas, first of all, are the area covered by these bottom trough surveys, coordinated internationally same trawl, same methods, everything comparable. And so the cluster analysis identified these different areas that had a similar change in functional groups over the 15-year time period. So there are 4 of them. Then we looked at a number of environmental variables, and what we found was that what explained, first of all, the spatial and the temporal pattern were the levels of dissolved oxygen, the variability in sea surface temperature over the 15-year period, and also sort of mean annual landings. The Mediterranean is a bit difficult for fisheries landings. FAO collects landings, but because there are so many harbors, we actually don't have a good sampling program. So the landings data is a bit, so we used it at the level we thought it would be informative. It does inform you on where are the higher catches, but well, it has to be taken with care. But basically, it did identify that we had these spatial temporal patterns, and here what you can see is these relative biomass changes for the different functional groups. And then you can see here, for example, across the whole Mediterranean, the pelagic groups in these 2 areas basically increased. Here it did a little bit. Then the demersal functional groups, there's some increase and some decrease, and then the benthic groups, well, in 3 out of the 4 areas basically increased. So there's quite a pattern in what changed, but it can be explained at least to some degree by these variables. So in this case, the functional groups provided the resolution at which we could look at the changes in the food web. So it was a means to actually capture the food web and then look at the changes. Now it's something completely different. I've also been working over the last 15 years on acoustics, and one thing I wanted to do is to say, what can we get out of acoustics beyond just single species stock assessment estimates? And so I've been working on multi-frequency acoustics, and some of you know how acoustics work. So we have a vessel that's got the echo sounder, and then we get an echogram, and if we have several frequencies, we get an echogram for every frequency. And basically what we can do with that, we can look at the backscatter at the different frequencies, and very handily, different types of organisms have different, what's called a frequency response curve. And that basically depends on the shape and the size of the organ that's most reflective, that has the density most different from water. So in case of fish, it's the swim bladder, if they have one, because if they don't, then they don't reflect a lot. And in case of a zooplankton or even air bubbles, so it's air bubble in a zooplankton cannot be distinguished on the echosounder. But basically, it provides a way to use this information to extract the signal from different groups. So in this case, what we did is we then identified prey functional groups, in this case I would call them, because we then have a zooplankton, but it's in quotes because we cannot distinguish, as I said, air bubbles, if they are of the same size. Then we have a small pelagics, and in our case, it's mainly horse mackerel, blue whiting, anchovy, sardine, and sprat, and then we have a mackerel which doesn't have a swim bladder. And basically, using, again, a 15-year time series of acoustic data, so which is then spatial temporal, we applied empirical orthogonal functions to map the different prey distributions. And this sort of the average stable map you can get from that, where we can now look at where are the different prey groups distributed, and as you can see here, so this is for the surface layers. You can do it by layer, or you could do the whole water column, whatever you're interested in. So this is just surface layers, and we can see that here the zooplankton is more dominant along the shelf edge. So this is France, and this is sort of, the shelf edge is about here. And here we have an area where there's a big river coming in, so there's also sort of a bloom of zooplankton. And then quite a different distribution we get for small pelagics or fish with a swim bladder, which are more closer to the coast at the time of a survey. So this is a spring survey. So basically, using acoustics, we've been able to extract the signal which informs on functional groups. Well, it's groups of individuals with similar acoustic properties. So that's not exactly an ecological definition, but it allows you to get towards something which is on a higher level than just the species level. And I think it opens a lot of opportunities and possibilities to use acoustics, because I know a lot of people are actually collecting these data now, and it's using acoustics without making use of any identification data. It doesn't require identification data, but it requires data collected at different frequencies. Okay. Now I'll be moving to the second part of the talk, which is about now we've got different ways of identifying functional groups. Of course, what we're interested in is how are they linked and how they change over time. So I showed you the example from Mediterranean, where we just looked at each individual group, how it changed, but we've also been working at actually the interactions between groups. So of course you have groups, and then you say, how do you actually identify the links? So the first approach we've been using is to say the expert method. Okay, we know that predators eat prey. Okay, so we can actually create models. In this case, it's a very simple food web model, where we say, okay, we go back to a very simple definition. Here are our piscivore predators. They feed on some prey, and the prey then have some basal resource. So this is just a food chain, and we define the relationships by saying, okay, negative impact because we feed on them, so they reduce. Whereas the prey have a positive impact on piscivores, on their predators, because of course by eating they can then reproduce, and the population can grow. But because we are looking at exploited ecosystems, of course, we also want to put on pressures. Where is the pressure coming in? In this case, it's a very simple formulation, because we say there's a specialized fishery that's on these predators, and then there's a fishery that's on the prey, which is a bit of a caricature, but it's quite true that pelagic fisheries and fisheries, because these are mainly demersal, are not the same fisheries. You don't use the same fishing gear. So these are mainly the pelagic trawlers, for example, if you want to think of it in what's this in the real world. And these are all the demersal, either trawlers or long lines or whatever nets you have. So basically, this is a very simple way of characterizing a food web, but then it allows you to look at the interactions. But of course, that's one way of saying what's going on. There are different alternatives, because you can have, so this is the core model, it's the same. But you can also say, okay, but we know that there are species that actually feed on different trophic levels. So this is the omnivory, and then you can look at systems where perhaps the top is too separate, so sort of wasp-raised systems. You can also say, okay, the fishery actually is not that separated. This demersal fishery has a negative impact on these preys, because there's a bycatch issue, and that's an issue that's become really important in recent years in Europe, where from this year, we have now, it started off being called a bycatch or a discard ban, but it's actually now being referred to as a landings obligation, which is sort of a positive way of expressing this, where for species under quota, all individuals have to be landed in. That's the legal position. And then you could think of another fishery where actually you have a fishery that's targeting simultaneously at two trophic levels. So basically, we first created these, you could call conceptual models, because I guess we are at the conceptual stage here, but then we actually used a tool called qualitative modeling to explore what happens when you have pressure changes. I'll show that a bit later. But here's just another way of creating models, just one step up. Instead of a food chain. In this case, we've said, okay, we know there might be actually two food chains. A pelagic one, which is the same, the piscivores, and then the planktivores, plankton, and then in this case it's just one level more, a sort of, could be phytoplankton. And then we have a second food chain, which is the demersal one, again, the benthos and the resources for the benthos, and then those that eat benthos, and then those that eat benthos. And basically it allows to have a bit more refined view on what the fisheries are doing, because in this case we have pelagic fleets, demersal and invertebrate fleets. And then this is just another way of expressing this again in a different way, and in this case, because this is actually for describing a real system. So this is more stylized, and this was a model we've used to actually look at a real system where we have different fleets. So they are defined by the gear we use, the dominant gear we use, because in France we have a wide range of fisheries, and they are actually, this is really stylized because a lot of vessels, they throw a pot overboard and then they go and put something else, and on the way, whatever, they do something else. And that makes it really hard to actually look at these fisheries and say, what are we doing? Because every vessel is its own fleet in a way. And so I find it very hard to actually talk about fleet dynamics. But basically, this is sort of stylized way of representing it. And then in this case, we also have here, we only have a link if that group is important for that gear or fish or fleet. And basically, I've used that view before doing a dynamic model to get a static view of what's going on in the system. So this is for the Bay of Biscay, which is just off France, the Atlantic. And so this is the conceptual representation, and then we've used landings and economic data to actually look at these links. So this is from the perspective of the fisheries. And basically, what we wanted to know is, what are the functional groups the different fleets depend on, and where do we get the money from? Where is the money coming in, and where is the energy? I've expressed landings in terms of kilojoules. And what you can see here, so these are just the different gears, so the different fleets. And you can see, for example, the mixed trawls, they fish right across the food web, because they get the energy from different functional groups. Whereas, well, pelagics, that's by definition, I mean, with that gear, you can't fish actually that widely. You get mainly the planktivores, but the proteins, it's the same. So this is the green. And then you have a different other. So basically, by first having the conceptual model and then using that to analyze the system, we can get a view of where's the energy coming from, which are the big players. And so in this case, the mixed trawls, that's the dominant gear. So that's in terms of what's extracted by whom. And then, of course, for fisheries, what's more important is where do we get the money from? And so we looked at the fleet revenues, and there the picture is quite different when you're talking money. Because, so in this case, we have the different functional groups here, and as you can see, it's much more balanced where the money comes from. There are three groups, the invertebrates, so that's a lot of shellfish, where the benthivores and the demersal piscivores provide a lot of revenue for different fleets. So again, the mixed trawls, they get the money from these three groups. And then, for example, the nets, they get mainly money from the benthivores and the piscivores. And then there are two groups that actually don't provide as much money. And basically, the group, the planktivores, which provided most tonnage, provided actually very well, not much income. And I guess that's quite a common situation, that the pelagic fisheries are huge. I mean, small pelagics are huge, but in terms of economy, it's not that important. So basically, in this case, the functional group approach, so this is a static approach, because I've used data for 10 years to get average estimate out of this to actually get the view of what's important and who depends on whom. So this is not a food web, but it's how is the economy in the fleets depending on these. So in this case, the functional groups were a useful way of actually structuring the analysis. Now, the next step is then to do actually the dynamics. And here I'll be talking about the different approaches we've been using. The first one is the qualitative modeling I've already mentioned. And then we've also been doing a quantitative modeling, and I'll be looking at presenting two kinds of results for an ecopath model, and then also a statistical approach, state space modeling. And for this modeling, of course, we come back to the data, the time series I've already used before in terms of ecosystems, so the trawl surveys, and the pressure time series. They are what the fishing does, the fisheries, but also the environment, so the temperature, for example. So those are the data that allow us to fit the model or to parameterize the models. Okay, the first one is an application to Georges Bank. Actually, in that study, we had 3 applications, but I will show you one because we compared. We compared using the same approach for different ecosystems, North Sea, Bay of Biscay, and the Georges Bank, in order to sort of get more general insights. But here I'll just show the Georges Bank results. So basically, I'm coming back to the model I've already showed you, the 2 food chains. And the questions we were asking here is, can we identify the main pressures that have actually been on the system and that changed the system? Can we actually, looking at the ecosystem, identify the main pressure drivers here? So the way we did this is to use qualitative modeling. So basically, for each system, we identified what changed over the time period we're looking at. So we identified that in general there was changes in fishing pressure and then changes in primary reduction. So these are the red ones. So basically, over a couple of decades, this changed and then the pressure changed. And so using qualitative modeling, which is also called loop analysis, and within that the tool is called press perturbation. It's an analysis that's carried out at equilibrium and then changing one at a time the different state variables. In this case, you can predict. So it's a permanent change of one of the variables, and how does that feed through direct and indirect effect towards the new equilibrium? So what you're looking at is the expected direction of change. Not how much, but just in which direction is each of the different functional groups expected to change. And in some cases, you cannot make predictions because direct and indirect effect can cancel. And then, of course, it's not possible to say qualitatively which direction it will change because it will depend the relative forces of each. But basically, that's the tool. So what we've done is, the first step is by decade to identify the pressures. So in this case, fisheries pressure high, medium, high, low, low. And then pelagic fisheries were also higher at the beginning, lower at the end. And for primary production, we have a went round. And then we do the predictions for the 3 groups only, because that's where we had the data we could compare predictions with. So basically what you predict is whether the biomass for the functional group is going to should have increased, because when you go from one decade to another, there's a change. So from high to low, the pressure decreases, here the pressure increases, and here it decreases. So you use that change, increase, decrease, to actually make the prediction. And so it means that because of this decrease, you predict there should have been an increase in total biomass, and then you can also predict something which is related to mean weight or life expectancy of a group. So that's what's called E here. And the stars are where it agrees with the data, but I'll show it here again, because then using these long time series from bottom trawl survey, which we have been carrying out for decades, and that's where you see you really need long time series for actually starting to see something and to to try and entangle effects. What we see is that in terms of biomass for the three groups, there was agreement between expected change and observed change for Bentivos in all, and then for mean weight, in this case for all decades, in some decades. So basically, the modeling was done based on what we thought what changed, and then we compare this to the actual data. And of course, the question then is, if there's agreement between the predictions and the observed time trends, does that mean your model representation is correct? But I guess that's the conclusion we would like to draw, that the model and the pressure changes represent what happened. But this is on a very qualitative level. We didn't say, we are not saying one change in this equals whatever, 3 change in fishery or whatever. This is on a very high level, qualitative level. We're interested in predicting changes that don't depend on the actual amount. And so I think for that, this kind of approach is very powerful because it allows you to predict independent of knowing the details, but it allows you to say what you'd expect the direction of change. So it provides insights and allows you to identify, okay, it seems likely that what we thought happened actually had an effect. Okay, then I've just talked quite a bit about qualitative modeling. The question, of course, is do we gain anything if we would do quantitative modeling? And a very common approach for food web modeling is EcoPath. I guess most of you know about it, perhaps have used it even. That's become a standard, I would say, in food web modeling. If people want to do a food web model, very often they turn to EcoPath. Of course, EcoPath, I mean, the qualitative modeling, that takes you 2 minutes to do. The EcoPath model, it's not 2 minutes. So for me, the real question was, do we really need an EcoPath model? Do we need one? Well, I guess you would answer, it depends on the question. But if our question is about what are the sensitive functional groups, or given the changes we know are happening, which are the groups we should be monitoring, because that's where the changes are. So in this case, our question was, do we need an EcoPath model to identify the functional groups we should be monitoring to see future changes? So we basically said, okay, we come back to our generic model. It's a little bit different from before because we've added a top predator here. We had an EcoPath model, an existing one, but we sort of restructured it a bit so it would match. Well, I don't know whether you think it matches, but basically it's supposed to match. So this is just drawn so you can see the two sides, but basically it's flipped around. So this is the benthic side, the demersal side, and this is the pelagic one. But basically the two models were built to be similar, where this has a lot of details, a lot of data, took a lot of time to do. And then the question was, if we now look at changes in drivers and pressures, what are the two models predicting, and do they agree? So so in this case, again, we compare the predicted direction of change, not in absolute values. And in the qualitative model, this is done using press perturbation, and for EcoPath, it's done through variation in parameter values to actually have this scenario, the different scenarios. And then what the result was that, so these are what we call robust qualitative predictions, because all predictions that don't depend, that are sure, for sure, it's going to change in that direction, like an increase in demersal pisovers, will have a negative impact on their demersal, bentodemersal prey and the pelagic prey. So, and then, so we did this comparison, and basically what this shows is that indeed there are some predictions, and they are borne out by using a quantitative model that are the same, even that you can obtain just as well with a qualitative model in 2 minutes, that this negative effect and the bottom-up effect of primary production on planktivores. Well, I guess you will tell me that actually I wouldn't have to do this anyway, because that's well known that in any system, because this is a result that's true for any system that can be described by the model we used. There's nothing particular about it, about the Bay of Biscay. It's just a general property if that's the structure of your food web, and if those are the pressures, that's what you expect to see. Whereas this is doing all this, the extra groups, the extra species. So basically, for those, but this is actually quite important, because it does tell us that if we want to see future changes, the groups we need to monitor, those are the groups with the demersal piscivores and then the planktivores. So basically, there are some insights you can gain from using quantitative models, but at the higher level, with higher level questions, what are the groups that are sensitive, which are the groups you should monitor, you actually don't need a quantitative model. You can do it qualitatively. And then it applies to any ecosystem that can be described by such a structure. And for me, that was quite an important result, because it just shows you, and I think that, I guess it's a general lesson, that depending what your question is, you're better off starting to think about what level you want the answer before you spend several years creating a quantitative model, because it could be that the answer you want is something which is on a qualitative level enough, because you want to identify important groups, or you want to identify just which direction it goes, and the actual level doesn't matter, because it's not as if EcoPath would be. Of course, EcoPath will provide the quantitative answer, but who knows whether that's a true answer? You don't know. But you've put in all of your information, and that's what it gives. But whether the actual change is 20%, 30%, or perhaps 55%, I don't know. But basically, I think the basic lesson here is the functional group approach allows you to structure the food web and the pressures. The fleets come into that. And then, depending on what your question is, you can use simple models to actually the qualitative approach. And rather than spending time on the parameterization, because it's so fast to do, you can just look at the effect of model structure. Because in the qualitative approach, actually, what I've showed you before, you saw the different alternative models for the simple food chain model. The links identify the structure, and you can add or remove links, and that's just a different model. Basically, instead of saying there's a little bit of interaction, you'd say there is one or there isn't. Basically, it boils down to that. But you can explore the effect of model structure, which is very hard to do with the quantitative models. And usually people don't have 3 different EcoPath models, which are quite different, to actually say, are the results robust? Okay, now I come to the last kind of models, state space models. So these are statistical models. And one study we've carried out is where we've used for describing the dynamics of functional groups. So that's the biomass. We use the Gumpert process model, where we have a biomass, and then we have a growth function. We have density dependent part, density independent part, and then some process error. And then we have an observation model, which just describes the relationship between observations and the actual underlying system. And then we have this kind of observation error. And basically what we've done here is we said, okay, we want to use this approach to actually identify the links. Before, I said, in the work I showed before, it was a priori, we defined links. In this case, it's not. We say we want to let the data tell us where the links are between groups. So basically, there are alternative links, which leads then to alternative models, so that you can identify different model variants. For example, if you have 2 groups that have no biological interaction, but are simply linked through the process error, so you just have a correlated process error, so it comes in here. Or you say there's an interspecific competition, so it's via this parameter that it's identified. Then you could also say there's nothing that links 2 groups you look at, or 3 groups, or whatever, but it's basically because of your observation process. And I think it's an important thing to remember. The way we observe the ecosystem, whether it's trawling or acoustics is very much linked, because the way you use the acoustic data, the acoustic energy is assigned to one group or one species. Actually, there's a total energy and you apportion it, so it's correlated. If you put too much to one, it's negative, it removes it from the other one. So there are correlations. And I think trawl data is also, you have correlations between species in a way. So basically, that could come in here, or the two are not linked. And basically, the way we've used this is to fit alternative models, so these, and then look at the parameter values. So, and we've used that for a very simple case. So this is just a two species case, not a functional group, but two species for the moment. And we've used this very long time series of landings for anchovy and sardine, and probably you know there have been many explanations and debates about the interactions and why those do we fluctuate, you know, one up, the other down, and all this kind of stuff. And so what we said here is, okay, let's see what the models tell us. So it's a statistical approach here. It's not ecological. And basically, using then model fitting criteria, we identified that for the different, we used 5, but for the different ones in general, it was the model that actually brings in the correspondence with negative correlation via the environment. But of course, it's a statistical model, but it's just a way to identify an explanation for the links. It's not a mechanistic model, it's a statistical model. And right now, we are actually working on using this approach for the more complex models I've showed you before, the food web models with more groups, not just two species, but more groups. We are, again, for the Bay of Biscay, because we know so much about it, I quite like to come back to the same system I've already looked at with a different tool and then be able to compare what does this kind of approach allow us to do, which we can't get from a different approach. So in conclusion, what I've showed you, we've used various methods, and there are probably other methods for defining groups, where the main aim is to use these functional groups to summarize an ecosystem, to summarize a food web, to describe that. Then, as I've shown you, there are different ways of actually modeling the interactions, where you either define a priori what is a link, and then you try to find the data to fit it. And there you can go from qualitative to very quantitative, and I think all the way in between. But I would argue, whatever you do, whether it's for functional groups or for the modeling, it will depend on what your questions are. Why are you doing this? What questions do you want to answer? And then, of course, as well on the data you have. But for me, one of the critical issues here is about how model structure. What complexity do you need for your question? And I think it's not easy to find an answer. How complex? Well, I would say for me, I want to be as simple as possible, as simple as I can get away for a question. I guess some people go the other way around. They come in from the complexity side. But for me, I come in from the simple side, and I want to know how complex do I have to go in terms of the model structure, and then how can I identify the links. So as I've shown you, what I'm working on right now is to use more statistical approaches to identify links, and not a priori force them and say this is what it should be, but be able to have dynamic links and fit it to data. Okay, thank you very much.
She shows all of her co-authors for all the papers that she did.
What papers I've shown here, yeah. Yeah.
So I was curious, you chose trophic breadth, I guess, to create your trophic groups. Do you guys consider adding other traits in defining your functional groups?
No, because why we did the groups is because we wanted to look at food webs. So that was our main motivation here. That's why we looked at trophic groups, because we are interested in how are the food webs perturbed by fishing and also driven by the environment. I guess that's why we didn't look at our ones. But it depends on your question. But for us, it was a food web question. Because we know fishing fishing is coming into the food web. I mean, that's why also I did this study more. How do the fisheries depend on the food web? But but because I work in the fisheries environment, interested as fishery is the main driver, and then how do the others come in?
I have a question, and
Yes.
a comment and a question. First of all, I appreciate the notion of a hierarchy of models from sort of conceptual to full quantitative. And oftentimes we either go one way or the other, full direct, as opposed to actually thinking about things in that way. My question is this: you had one slide where you talked about the concept of weak interactions between species, right? And in many ecosystems, and I'll take the Gulf of Mexico for example, if you look in the diets of any particular predator, there's a large number of items, right? And so they're weakly dependent on any particular one. And so, we focus on individual species and, just because they're iconic or whatever. But I wonder if you could comment on, the relationship between the strength of the obligate interactions and the modeling level that we would actually try to look at in terms of, either breaking it into functional groups or even trophic levels.
Yeah, I guess you already start giving the answer I would give, because that's because of this weak interactions or species having similar weak interactions. That's why we went towards the functional group level, so that to say, okay, as long as one of the species is present in that group, the predator will eat. And that's why if we just look, the prey is on the functional group level, then that's enough. We don't need to actually consider individual links. But that's one answer. But the other was also, that's why we use this qualitative modeling, because it's easy to say, what if the link was strong enough to have an impact, or if not, then we just remove the link. And then you can look at what changes you'd expect. So basically, I think, for me, I started off my career. My first project was on a multi-species model. Basically, at the time already, 18 years ago, it was very fashionable. Everybody said, oh, you can no longer do single-species stock assessment. No good. That's not taking into account the ecosystems. I thought, okay, you're still, I think, which is strange, we're still there, basically. But my first project was about, okay, the Celtic Sea, which is between France, Ireland, and Britain. For that ecosystem, what do we know about interactions? And I did a big study on stomach contents, spatial temporal variability of stomach contents, and it got all these effects. In one season they ate one thing, the other season they ate another thing, and how on earth do I put that into my model, that the seasonality? And because we don't manage, basically that's where I came to the conclusion. A lot of weak links, but they're actually not weak necessarily all year round. But how do you put that into a model? Actually, I decided I didn't know how to do that, and that because of that, I didn't have to do a multi-species stock assessment model, because that was the objective, a multi-species stock assessment model. I just didn't believe, but that's my personal, that's why I believe that I could do a multi-species stock assessment model, which I would believe the results. Because of this spatial and temporal variability of interactions. And I think EcoPath provides a stable average view, and in a way it makes you forget that the links are actually dynamic in time and might be seasonal, and it doesn't allow that. And at the end of the day, I'm not sure what we're actually describing with a model like that, whether it's anything that's real. So basically, it boils down to the questions. For me, the issue was then to say, okay, for stock assessment, I don't believe that it's going to be better if I do all these many interactions which are going to be very uncertain. So one route is to go functional groups, group them all, and then try on that level to evaluate how the food web changes and how the pressure goes through. And the other one is to say, okay, we don't actually need for stock assessment, at least for certain species, we don't need everything else. Or not that we don't need, but actually we cannot do much better than putting it in the error term. I guess that's for me, but that's a personal, I think these approaches are I think it's quite personal, what you think is a better route depending on what you're trying to do. Because I don't think there's no correct or wrong answer here. It's very much driven by what's the question, what data you have, and yeah. I don't know. It's a long answer for.
It's a complicated question.
It's a complicated question. In a way, there have been loads of discussions. When I came into the field, ecopath wasn't recognized as a valid way of doing things. I think, if I may summarize it like this, people question that this was actually doing something useful. It has become now a standard way of doing things, but I think perhaps too standard. I think it's very useful before you set off doing whatever kind of model that you really think about whether that's what you want to do and whether the assumptions behind any of the methods are actually suitable or you want to make them for the question you're asking.
Are you aware of anyone who has looked at morphology, mouth morphology, the size of the fish, and actually compared it with diet data?
Well, we did that. I was a bit fast. We did actually compare it.
You use gut content?
Yeah. We had actual diet data from several years. I mean, quite a time series. Yeah, basically we went out to measure the fish, and then we used the gut content. But the gut content, as I say, the mouth and all that, that's the potential. And the gut content, of course, is the realized, which depends on how the prey stocks are doing and what time and where you actually collected your stomachs.
Right. So did you...
And that's where I showed you we had 28% of the variability in gut content could be explained by the groups. That was the result. And if you only group the species, the individuals by size, it only explained the 12%. So that's
you could compare the predator to prey weight ratios relative to the gape size, right?
okay.
That's probably going to
Okay.
tell you a lot about.
Yeah, we didn't do that. Yeah, to go further to actually validate what. No, we didn't do that.
It appears to me that it's not, it's not just the size of the mouth, but also the shape of the mouth.
But that's part of the
Yeah,
characteristics.
Oh, okay.
Yeah. It's a whole list. It's not only the mouth. It's basically the individuals are grouped based on several measurements with respect to the mouth, with respect to
Yeah.
and then also gut length and a whole list. I can.
Oh. So did you use like an AIC or something like that to determine what was the morphological characteristics that was most important?
Okay, no, because we didn't go this way. No, because in a way what we were. I just tried to put this up. Where is it? Here. Yeah, okay. This is just the list of the different measurements in terms of also the body shape, because a lot of parameters contribute to an individual fish's capacity to feed on different prey. But in a way, our reasoning here was to say, okay, we do these measurements. We use statistical analysis to group individuals with similar measurements. And then we basically use the diet data to validate. But we didn't go the other way around to say, okay, because that's another question. You could use the diet data to identify which are the more important ones. Right. But the list was based on the literature, what people thought was important. But it's true, I'm not sure people have gone the other way around saying you use analysis to identify the four most important parameters. I'm not aware of, perhaps that exists, but I don't know of any study. But that would be another way of going about it, yeah. Yes?
When you were defining your functional groups, did you take into account like the ontogenetic shifts? I know there was something there.
Yeah, it's here.
Okay. Yeah.
It's here. In this study we did, because, some of the traits, of course, a lot of traits depend on length. So we're basically standardized for length, and then length came back in as a separate, because of course all these proportional things, head size and all that, it's relative to length. So we first removed the length effect and then added it back in, and that's why on the right hand side you see the different, what it indicates is this is the length distribution of individuals. Yes, in this study we did. Because of course, yes, most species do have a change in morphology, in actually relative morphology, which allows them to feed on different prey. So we did. But of course, that's more difficult to use afterwards, because when you want to create, you compare results to data, having the length in there makes it more complicated. That's why in the second study we didn't consider length. But of course, we do know that actually length is a very structuring variable for.
The second and third species down are monkfishes,
Mhm,
and
yeah.
so they're all head, right? And so
Yeah.
obviously, as they get bigger, I mean, you can see that they're changing their function.
Yeah, because they are quite different species. There's the second, third are monkfish, and then the fourth one is a very small species that's flat in this direction and only get that big. So this is, in a way, they are ordered sort of to try and separate into groups, but there are very, very different morphologies behind there, very different species. But these are the dominant species in the Celtic Sea, so that's why we could get enough individuals actually to measure them. Yeah.
I'm curious about your actual individual clustering techniques, and specifically how you can have a size class represented in multiple functional groups that you have here. How does that happen?
It's because what comes into the analysis is not a measurement on the species level, but it's a measurement on the individual level. So you cluster individuals which have morphological measurements and the size variable. So that goes into the cluster analysis. But actually, I didn't tell you, this was actually very complicated, because we did this first clustering, and then it came up with loads of clusters, and then we said, oh, this is too much. And then there was a bit of a manual manipulation to reduce this and say, okay, yeah, but these are basically similar, we know this. So, but basically, in this case, we cluster individuals, whereas in the second study I showed you, we clustered species, because each species, we measured several individuals and then averaged the traits by having first removed the size effect. So that's a different, basically, yeah. But I think what's limiting, was a PhD study, what's limiting here is, of course, the amount of work you can do and how many individuals you manage to get, and wherever you actually manage to get the full size range and all that. So,
That's why we have matrix students.
well,
How about the use of individual-based modeling approach integrated in things like eco-bag modeling? Let your creatures loose, go to the habitat, they have the prey field, and validate your size from that approach. Has there been any thinking that way?
I haven't, because for me that sounds like a lot of work. Because of this capacity of individual, I guess you can define rules that they're very flexible, but then you really need a spatial temporal model that can actually model the seasonality, because we are in but I haven't seen anybody, because what I know what people do is based on size only. They've done in their models, but I think size is not enough, basically. But I haven't seen any, but I could exist. I'm not. Basically, and I'm not sure what would you gain by doing that. I mean, it would be a lot of work. You gain that, but beyond that,
About lack of dynamics.
yeah, yes, but you need a lot of data, I guess, to actually be able to, in a way, parameterize then such a model or see what are the actual dynamics. I mean, in diet data, I don't know whether you collect any. Diet data is a lot. I mean, if you really do the cutting up and looking at it and identifying that, it's a lot of work. So what we had in Europe is that there were, right now, we don't collect that much. But in the past, people have put in a lot of effort. And when I looked at this database, I inherited a database from somebody. She was retiring, and she gave me a pile of paper like this and said, here, I'm retiring, you get this. Yeah, and there was the year of the stomach, but this was somebody else, which was in the Celtic Sea. And it just, because she went out on fishing vessels for years at different seasons, so it was a really beautiful data set. But once I analyzed it and I realized there was so much spatial-temporal variability in what the same species was eating at different times in different places. Okay.
That would be the reason to do algorithms, right? Is to capture the statistical differences.
It would.
among
It would, but it does mean you need, I guess once you have the data, you can say, why not do it and actually make best use of it. It's true. I didn't do it, but we do have some, good data we could be used to actually do that. But actually, no, now thinking about it, I know, the Norwegians have a model like that, and I forgot. But their model only does, so it's called Novicom, perhaps you've seen it. It's an individual-based model which is focused on pelagic species, so mackerel, herring, and the individuals, because they do these very long migrations, so it has a big aspect in it. They migrate, and then where do they overlap, and where do actually they eat each other, and where do they interact with cod and all that stuff. But I think they have a few species in there, and it's already it took them some time. So. And perhaps in that case, if you only look at the pelagic system, you can do it because you don't have that many species, and you do have really strong drivers. I mean, that's the beauty of pelagics. If you want to work on environmental drivers, at least in the systems I know, you need to look at pelagics because they're so driven by the environment. Whereas a lot of the demersal species are much more buffered because of the life cycle. But basically, so yeah, I have an example where we actually did it.
Yeah, the functional groups are a very practical way of looking at things, but you've got that other aspect where individuals that occupy similar niches will try to minimize your dietary overlap or use of space. So how do you deal with that in setting up the functional groups?
Yeah, as you've seen, we have always because there's space in 2 dimensions, you have space like this and you have space in depth. And basically all the work we've been doing, we've always considered in space, and that's why when I showed the functional groups as well for the Mediterranean, we do interpret them in terms of are they pelagic or demersal, because that separates in the systems. And in a way, when I showed you the 2 food chains, that's our thinking is the minimum spatial aspect you need to consider is the vertical dimension. Because, I mean, there are some species that are migrating, but there's a real vertical distinction. If you don't want to do space in the horizontal, at least you do need to take that into account. And that's quite easily taken into account because, well, to some degree, more easily than the other dimension, at least in general. I think it's easier to decide to identify that as how to separate the groups. But basically, so far we've done that by looking at the groups, what are the species in there, and then it's interpretation. It's sort of a posteriori saying, okay, these are the pelagic groups, and these are the demersal groups, and these are the benthic groups.
Well, we've teased you long enough. Thank you so much.
Yeah.
And we have a seminar.
I was in spring.
Good luck with that.
My name is Megan.
Hi,
Graduate
Megan.
student here. I was hoping to join you and Steve for lunch, but
Okay, you won't be able to?
well, I was just talking about we have a lab, not a lecture.
Okay.
So
Did it work? I need to.
Yes,
Where do I sign?
I need your signature.
Here. Is it this one?
Yeah.
Okay.